Welcome to our video on the fundamentals of cryptography, part of the CompTIA Security Plus Guide to Network Security Fundamentals. In this session, we'll explore the core concepts of cryptography, including the definition, key algorithms like hash, symmetric, and asymmetric cryptography, and the various ways cryptography is applied in network security. We'll also discuss the benefits of cryptography, such as confidentiality, integrity, authentication, non-repudiation, and obfuscation, along with some limitations and common attacks. Stay tuned as we delve into the fascinating world of cryptography and learn how it helps protect our digital information. By the end of this module, you should be able to 1. Define cryptography. 2. Describe hash, symmetric, and asymmetric cryptographic algorithms. 3. List the various ways in which cryptography is used. 4. Explain different cryptographic limitations and attacks. Steganography is a technique used to hide the existence of data. It can embed hidden messages within image, audio, or video files by dividing and placing the data in unused portions of the file. One common method involves concealing data within the file's header fields or between sections of metadata, which describe the file's content or structure. This way, the hidden data remains undetected, providing an additional layer of security. Cryptography is like a secret code language used to keep our information safe. By transforming readable data, or plaintext, into a scrambled, unreadable format called ciphertext, cryptography hides information from unauthorized eyes. This transformation happens through encryption, where special mathematical rules, or algorithms, scramble the data. To make the data readable again, we use decryption, kind of like decoding a secret message. A key part of this process is the key, which controls how the encryption and decryption occur. Without the right key, the data stays locked and secure. So, cryptography isn't just for tech experts. It protects our everyday digital activities, ensuring our private information stays just that, private. Cryptography provides a number of benefits. Confidentiality is like a secret handshake. It ensures that only the right eyes see your information. Integrity keeps your data intact, guaranteeing it reaches its destination just as you sent it. Authentication acts like an ID check, confirming the identity of the sender, while non-repudiation makes sure that actions can't be denied after they're taken, holding everyone accountable. Lastly, obfuscation and security through obscurity keep your data safe by making it and its protections hard to figure out for anyone not in the know. Cryptography isn't just about security. It empowers trust and reliability in our digital interactions. Knowledge check. Layla has encrypted a document so that it can only be viewed by those who have been provided the key. What protection has she given to this document? A. Confidentiality. B. Integrity. C. Authentication. D. Obfuscation. The correct answer is a confidentiality. By encrypting the document, Layla ensures that only authorized individuals with the key can access and view its contents, keeping the information private and confidential. In the world of cryptography, we have different tools that work together to keep your information safe. First, there are hash algorithms. These create unique codes for your data, acting like secret fingerprints to ensure nothing has been altered. Next, we have symmetric cryptographic algorithms. They use the same key to both lock and unlock your message, just like a special key for a secret box. And then, there are asymmetric cryptographic algorithms. These use different keys for locking and unlocking, providing an extra layer of security, like having a lock that needs two keys to open. So, whether you're sending messages or protecting your digital files, cryptography acts like a digital superhero, safeguarding your information. Here are several variations of algorithms. First up, we have the one-time pad. Imagine you have a secret message like, hello, and a random key like, QWERT. You combine them using OTP, and it becomes, DLTBY. But remember, you can only use this key once. Next, we have stream cipher. It's like playing a game where you replace each letter in your message with another. So, HELLO might turn into IFMMP. Then there's block cipher. This is like taking a whole sentence and mixing it up at once. So, how are you could become UOH raw yo. Lastly, we have the sponge function. It's like blending up ingredients to make a smoothie. You can put in any amount, and you'll get a variable length result. So, whether it's swapping letters, mixing up sentences, or blending texts, cryptography is like a cool digital puzzle keeping our messages safe and sound. Think of a hash algorithm as a digital fingerprint for your data. It's like a unique stamp that ensures your data is unchanged and genuine. Now, this fingerprint, also known as a digest, represents what's inside your data and helps us compare it to make sure everything's in order. But here's the cool part. Hashing is a one-way process. Once your data is hashed, you can't reverse it to see the original. It's like a one-way street. Now, when we talk about secure hash algorithms, we're talking about digital locks for your data. Secure hash algorithm, SHA, is like a super strong lock, and there are others like RIPE-MD and Whirlpool that also keep your data safe. So, whether you're sending messages or storing important files, hashing acts like a digital security guard, making sure everything stays exactly as it should be, safe and unchanged. Symmetric cryptographic algorithms. Imagine having a magic key that both locks and unlocks a treasure chest. That's what symmetric cryptography does. It uses the same key to keep your messages safe and then unlock them when needed. Private key cryptography. Think of it as having a secret code between you and your best friend. You both know the code, but you keep it private. That way, only you and your friend can understand your messages. Strong encryption. It's like having an ultra-strong lock on your diary. If you keep the key safe, no one else can peek inside. It's just for you and your trusted friend. Strong algorithms. Advanced Encryption Standard, AES. This is like the Fort Knox of locks for your data, super tough to crack. Blowfish and twofish. These are like having extra layers of protection on your digital treasure chest, making it even harder for anyone to break in. So, whether you're sending secret messages or keeping your personal stuff safe, these concepts help make sure your digital world stays secure. Imagine having a treasure box full of secrets that you want to share with friends. You use a magical key to keep it locked and safe, like a secret password known only to you and your friends. With symmetric algorithms, sharing this key among many friends can be challenging, like trying to share a secret password with too many people. But with asymmetric cryptography, you have two keys: a public key for sharing with everyone and a private key just for you. It's like having a digital lock with two keys, one for everyone to use and one secret key only you know. The public key is like a digital welcome mat, open to everyone, while the private key is your secret weapon, known only to you. This setup ensures your digital space stays secure, allowing you to share and protect your secrets effectively. Imagine you have a special lock and key system for your digital secrets. You have two keys, one that you share with everyone, the public key, and one that's just for you, the private key. The public key is like a digital welcome mat, open for anyone to use and access your secrets. But the private key? That's your secret weapon, known only to you, like having a hidden key to your digital treasure chest. The cool part? These keys can work in both directions, making it easy to share and protect your digital secrets with ease. RSA and ECC are two cool ways to keep your digital secrets safe. RSA, like a tricky math puzzle, uses big prime numbers to create a secret key that's hard to crack. It's like having a super secure lock for your messages. On the other hand, ECC is like sharing a secret shape and point with your friend to create a key. Because the keys are smaller, ECC is faster and loved by modern devices. So whether it's the math magic of RSA or the speedy ECC, your digital secrets are in good hands. Imagine you're sending a secret message to your friend. and you want to make sure they know it's really from you. That's where the digital signature algorithm, DSA, comes in. It creates a special digital signature that verifies you. It shows your friend that the message is indeed from you. Prevents denial. Your friend can't say they didn't receive the message from you. Ensures integrity. It proves that the message hasn't been changed along the way. Now, when it comes to exchanging secret keys securely, there are cool methods like Diffie-Hellman, DH, Diffie-Hellman ephemeral, DHE, elliptic curve Diffie-Hellman, ECDH, and perfect forward secrecy, PFS. These methods make sure that only you and your friend can understand the secret keys, keeping your messages safe and sound. Knowledge check. Which algorithm uses the same key to both encrypt and decrypt data? A. Asymmetric cryptographic algorithm. B. Hashing algorithm. C. Pairwise keypair algorithm. D. Symmetric cryptographic algorithm. The correct answer is D. Symmetric cryptographic algorithm. Symmetric algorithms use the same key for both encryption and decryption. This means the sender and the receiver must both have the same secret key and keep it secure. Examples include AES, Advanced Encryption Standard, and DE, Data Encryption Standard. Symmetric cryptography is efficient and faster for encrypting large amounts of data but requires secure key distribution methods, as both parties need to have the same key. File and file system cryptography involves using encryption software to protect data. You can encrypt or decrypt individual files using file-level encryption, or protect groups of files by leveraging the operating system's file system capabilities. There are various third-party tools available for encryption, including GNU Privacy Guard, GNUPG, AXCrypt, Folder Lock, and VeraCrypt. Microsoft Windows offers a built-in encrypting file system, EFS, which integrates tightly with the file system, making encryption and decryption processes seamless and transparent to the user. Disk encryption involves using full disk encryption, FDE, to protect all data on a hard drive. A well-known example of this is BitLocker, which is included with Microsoft Windows. BitLocker encrypts the entire disk, including the Windows registry, ensuring comprehensive data protection. Additionally, volume-level encryption can be used to secure specific sections of a drive, known as volumes, which are accessible by users and have an associated file system. This layered approach enhances data security by protecting both entire disks and individual sections. Database encryption can be done in two main ways. The plug-in method involves adding an encryption module to the Database Management System, DBMS. In contrast, transparent data encryption, TDE, handles encryption and decryption within the database engine itself. TDE is easier to manage because it doesn't require any additional packages or changes to the database, engine, or DBMS code. This makes TDE a straightforward and efficient option for securing database data. Cryptography can be integrated directly into hardware, offering a robust layer of security. This approach includes embedding cryptographic features within the hardware components of devices like USB drives and standard hard drives. For instance, when cryptographic functions are built into the hardware of a USB device, all data saved onto the device is automatically encrypted, safeguarding the information seamlessly. Moreover, certain advanced USB devices equipped with hardware-based encryption allow administrators to remotely control access. They can prevent unauthorized access, disable a user's access, or even command the device to erase all its stored data through a self-destruct sequence. This direct integration of cryptography into hardware ensures a high level of security with minimal user intervention, making it an efficient and reliable method for protecting sensitive data. Self-encrypting drives are special drives that protect all data written to them. During power-up, the drive and host device perform an authentication process. If authentication fails, the drive can be set to deny access or even delete the encryption keys, making all data permanently unreadable. A hardware security module, HSM, is an external device used for cryptographic purposes. It has a built-in key generator and key storage, and it speeds up both symmetric and asymmetric encryption processes. A trusted execution environment is a secure area within a computer that protects the confidentiality and integrity of code and data. It's like having a secure vault inside your device. The Trusted Platform Module is a globally recognized standard for such secure areas, offering various cryptographic services. It includes features like a random number generator and supports asymmetric encryption, allowing it to create public and private keys. On Apple and Android devices, this secure area is known as a secure enclave. A blockchain is a shared, unchangeable record that helps record transactions and track assets in a business network. It works by allowing a group of computers to regularly agree on the true state of a distributed ledger, ensuring everyone has the same information. There are different types of blockchains. A public blockchain is open to anyone who wants to join. A private blockchain is restricted to certain users, and a federated blockchain combines both public and private features, making it useful for organizations that need a bit of both. Adding cryptography is essential for securing low-power devices and applications that need fast response times, but it's challenging. These devices have limited resources, and cryptographic algorithms need both time and energy to work. This creates a balancing act between maintaining security and ensuring the device performs well. The key is to find a way to protect the device without overloading its limited capabilities. Two common cryptography attacks are algorithm attacks and collision attacks. Attackers use various methods to get around strong encryption, such as known ciphertext attacks, where they analyze the encrypted data to find patterns, and downgrade attacks, where they force a system to switch from a secure mode to an older, less secure one. Statistical tools can help attackers find these patterns in the ciphertext, which can then reveal the original data or the encryption key. Imagine you're using a special formula to create a unique code for each message you send so that even if someone else writes the exact same message, their code would be different. However, in a collision attack, someone tries really hard to write a different message that ends up with the same code as yours. When they succeed, it's called a collision, just like when two cars end up in the same spot and crash. Now, there's another interesting concept called a birthday attack, which uses the idea from the birthday paradox. This paradox says that you only need 253 people in a room for there to be a 50% chance that two of them share the same birthday. Similarly, in cryptography, a birthday attack means finding two different messages that end up with the same code quicker than you might expect, just like finding birthday twins in a large room full of people. Quantum computing might sound like something from a sci-fi movie, but it's a real technology that uses the rules of quantum physics. Instead of using bits like traditional computers, which can be either 0 or 1, quantum computers use qubits. These qubits are super special because they can be both 0 and 1 at the same time. This allows a single qubit to perform two calculations at once. However, this cool feature also presents a big challenge for keeping information safe. Quantum computers can solve certain problems very quickly, like factoring large numbers using many atoms simultaneously. This means they could break the codes that keep our digital information secure today. But don't worry, scientists are already on it, developing new types of security called post-quantum cryptography. These new methods are designed to be safe from quantum computers, ensuring our data stays secure even in the quantum future. Knowledge check. Which type of encryption would protect all data on a hard drive, including the installed OS? A. FDE. B. SSED. C. TXPM. D. HRHS. The answer is a full disk encryption which protects all data on a hard drive, including the installed operating system, by encrypting the entire disk. This means that all files, folders, and system files are encrypted, making them inaccessible without the correct decryption key. For example, if you have a laptop with FDE enabled and someone steals the laptop, they won't be able to access any data on the hard drive without the encryption key. Even if they remove the hard drive and try to access it from another device, the data will remain encrypted and unreadable. Self-assessment. Rate your competence of the following module objectives on a scale of 1 to 5, where 5 indicates you have full confidence in your competence of that objective and 1 indicates you have very little confidence in your competence of that objective. If you self-score less than 4, you should consider reviewing the module and related exercises. 1. Define cryptography. 2. Describe hash, symmetric, and asymmetric cryptographic algorithms. 3. List the various ways in which cryptography is used. 4. Explain different cryptographic limitations and attacks. Congratulations on completing Module 3, Fundamentals of Cryptography from Champa's CompTIA Security Plus Guide to Network Security Fundamentals, 8th edition. You've gained a solid understanding of cryptography, which is like a secret code that keeps information safe and secure. You can define cryptography and describe hash, symmetric, and asymmetric cryptographic algorithms. You've also learned about the various ways cryptography is used, from securing online transactions to protecting emails and messages. Understanding the limitations and potential attacks in cryptography, such as brute force attacks, is crucial for ensuring data security. Keep exploring cybersecurity, and don't forget to like, subscribe, and share this valuable knowledge with your friends and followers on social media to spread awareness about the importance of cryptography in our digital world.